Hello there, and welcome to the Science into Sleep channel. Tonight we are drifting into one of the oldest unanswered questions in all of physics. There is something filling the universe that no instrument has ever photographed. It has no colour. It carries no temperature you could measure with a thermometer. And yet, it weighs more than every star, every planet, and every cloud of glowing gas combined. In this journey, we will wander through the story of dark matter, from the first hints in spinning galaxies to the quiet laboratories buried beneath mountains. By the time we reach the end, the mystery will not be solved, but it will feel closer, warmer, and strangely restful. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. Let your shoulders drop and your jaw soften. There is nowhere else to be right now. The story ahead moves slowly, and it asks nothing of you except a willingness to wonder. We begin with something you already know without knowing it. Every object you have ever held has weight. A stone in your palm pulls downward. Water in a glass settles to the bottom. The moon tugs the ocean toward itself twice a day. Gravity is the quietest force in nature and also the most patient. It never stops pulling. It never takes a break. And across the distances of space, it is the one force that shapes everything large. Now picture the night sky on a clear evening, far from city lights. You might see a few thousand stars. Each one belongs to our own galaxy, the Milky Way. But what you see is only a fraction of what holds this galaxy together. The visible material, all that shining starlight, accounts for a surprisingly small share of the total gravitational pull needed to keep things in orbit. Something else is present, something heavy, something that refuses to announce itself with light. This is not a new suspicion. For nearly a century, measurements have pointed toward an invisible ingredient woven through the fabric of space. It does not glow in any wavelength. It does not block the light of objects behind it. It does not warm up or cool down in any way that our instruments can register. Yet it pulls. It gathers. It shapes. And without it, the galaxies we see would fly apart like sparks scattering from a wheel. Think of it this way. You are standing in a large, dark room. You cannot see the walls, the ceiling, or the floor, but you can feel a gentle slope beneath your feet. Something is shaping the ground under you, guiding where you drift. That slope is gravity, and the invisible substance creating it is what we call dark matter. It is the hidden landscape on which the visible universe sits. The numbers involved are staggering. For every kilogram of ordinary matter in the cosmos, there appear to be roughly 5 kilograms of this invisible substance. Stars, gas, dust, Planets, oceans, and every living thing together make up a modest fraction of the total. The rest is hidden in plain sight, if you can call something hidden when it fills every corner of existence. What makes this mystery so compelling is that it does not rest on a single observation. It emerges from dozens of independent measurements, each pointing the same way. Galaxy rotation curves, galaxy cluster dynamics, the bending of distant light, the faint ripple pattern in the oldest glow of the universe. They all agree. Something massive is there, and it is not ordinary matter. Tonight we trace that landscape from the closest clues to the farthest horizons. Every section carries a piece of the puzzle, and each piece connects to the next, like stones laid across a quiet stream. Galaxies are not still, they spin. The Milky Way turns like a slow wheel, and every star in it follows an orbit around the center. Our own sun takes roughly 230 million years to complete one lap. That means, since the dinosaurs disappeared, we have not even finished one full orbit. When astronomers first measured how far stars move at different distances from a galaxy's center, they expected a familiar pattern. Close to the middle, where most of the visible mass is packed, stars should orbit quickly. Farther out, where fewer stars shine, the speeds should drop. That is how planets behave around the Sun. Mercury races, Neptune drifts. But galaxies refuse to follow the script. In spiral after spiral, the outer stars kept moving at nearly the same speed as the inner ones. It was like watching a carousel where the horses at the edge spin just as fast as those near the pole. Nothing visible out there could be pulling them along, yet they held on. The rotation curves stayed flat where they should have fallen, and that flatness became one of the loudest whispers in modern science. Imagine a pond with a fountain in the center. The water nearest the fountain swirls quickly. Farther out, it should slow to a gentle drift. Now imagine it does not slow. Something beneath the surface must be pushing, something you cannot see from above. That hidden current is analogous to the gravitational pull of dark matter, spreading far beyond the visible boundaries of a galaxy. Vera Rubin and Kent Ford brought this mystery into sharp focus during the 1970s. They studied the rotation of the Andromeda Galaxy with careful precision. Their measurements showed that stars at the outer edge moved far too quickly for the visible mass to hold them. The numbers were clear. The galaxy needed more gravity than its starlight could provide. And the extra pull was not a small adjustment. It was enormous. This was not a problem limited to one galaxy. The same pattern appeared everywhere astronomers looked. Large spirals, small spirals, galaxies seen edge-on and galaxies seen face-on. The flat rotation curve became a universal signature, like a fingerprint, left at every scene by the same unseen presence. It was not a quirk of one system. It was a rule of galactic life. that demanded an explanation larger than any single galaxy could provide. Galaxy clusters offered another angle on the same mystery. A cluster is a gathering of hundreds or even thousands of galaxies bound together by gravity. Think of a swarm of fireflies circling the same lamp. Each one moves independently, yet something keeps the swarm together. When astronomers measured how fast galaxies were moving inside these clusters, the speeds were far too high for the visible matter to explain. The clusters should have flown apart long ago. Yet they held together, calm and ancient, as if something massive and invisible was cradling them. Fritz Zwicky noticed this discrepancy in the 1930s while studying the Coma cluster. He calculated the mass needed to keep the galaxies bound and compared it to the mass he could see. The gap was staggering. He used the term dark matter to describe the missing component. The idea seemed radical at the time, but the arithmetic was simple and stubborn. Between galaxies inside a cluster, there is also superheated gas that glows in X-rays. This gas reaches tens of millions of degrees, and at those temperatures, it wants desperately to expand and escape. The fact that it stays trapped tells you the gravitational well is deep. Even when you add the mass of the gas to the mass of the galaxies, the total still falls short. The cluster demands more weight than anything visible can deliver. Gravity can also bend light, and this bending provides yet another way to weigh the invisible. When a massive object sits between us and a more distant galaxy, its gravity warps the surrounding space. Light from the background galaxy follows those curves and arrives distorted, stretched into arcs, or even split into multiple images. This effect is called gravitational lensing, and it depends on the total mass along the line of sight, not just the bright mass. In some lensing systems, the strongest signal comes from regions where very little starlight exists. The weight is real, but the glow is absent. Lensing has become one of the most powerful ways to map invisible mass, because it relies on geometry rather than brightness. It does not care whether the matter shines. It only cares whether the matter bends space. Sometimes the lensing is dramatic. A single background galaxy can be stretched into a nearly perfect ring called an Einstein ring if the alignment is precise enough. Other times, a background source is split into multiple copies, each arriving along a different path through curved space. These multiple images can even show time delays. If the background source changes brightness, the change appears at slightly different moments in each image, because the light paths have different lengths. There is also a quieter form of lensing. Weak lensing does not produce dramatic arcs or rings. Instead, it slightly distorts the shapes of millions of background galaxies by tiny amounts that are invisible on a case-by-case basis. But when you measure millions of shapes and look for patterns, the cumulative distortion reveals where mass is concentrated between us and those galaxies. It is like reading wind direction from a whole meadow of grass rather than from a single blade. This statistical approach has become one of the most precise ways to map the invisible structure of the universe. The cosmic microwave background is a faint glow arriving from every direction in the sky. It is the oldest light in the universe, released when atoms first formed roughly 380,000 years after the beginning. Before that moment, the universe was a dense fog of particles and radiation, too hot for stable atoms to exist. Light bounced endlessly between charged particles, unable to travel far. When the temperature dropped enough for electrons to settle into orbits around nuclei, the fog cleared. Light was free to travel, and it has been traveling ever since. We detect it today as a gentle bath of microwave radiation. The expansion of space has cooled it from thousands of degrees to just a few degrees above absolute zero. That ancient glow is not perfectly uniform. It carries tiny variations in temperature, like a faint pattern pressed into the fabric of the early universe. Those variations are small, only about 1 part in 100,000, yet they are profoundly important. They record where matter was slightly denser and where it was slightly thinner at the moment the universe became transparent. Dark matter played a central role in shaping those variations. Ordinary matter was tangled up with radiation in the early universe. It could not clump freely because photons kept pushing it back, like wind scattering seeds before they can land. Dark matter, by contrast, does not interact with light. It began gathering into denser patches earlier, building gravitational wells that ordinary matter would later fall into. You can think of it like preparing a garden bed before planting. Dark matter dug the furrows. Ordinary matter filled them once the conditions were right. The temperature pattern in the microwave background records the moment those furrows were first taking shape. Scientists measure the heights and positions of peaks in that pattern with extraordinary precision. Each peak tells a story about the balance between gravity, pressure, and expansion in the young universe. The relative heights reveal how much dark matter was present compared to ordinary matter. This is one of the most elegant pieces of evidence for invisible mass. It comes not from watching galaxies spin or clusters hold together, but from the faintest light in existence. The microwave sky acts like a fossil record of a time when the universe was less than 500,000 years old. And written into that fossil is a clear message. Something with gravity, something that did not interact with light, was already at work. Now let us follow those early density patches forward in time. As the universe expanded and cooled, the gravitational wells deepened. Gas fell inward, heated up, and began to radiate energy away. In the densest regions, gas cooled enough to collapse under its own weight. The first stars ignited. Those first stars were probably very different from the ones we see today. The early universe had almost no heavy elements, no carbon, no oxygen, no iron. Cooling was harder, so the clouds that collapsed had to be more massive, and the stars they produced were likely enormous and short-lived. But they needed somewhere to form, and that somewhere was provided by dark matter halos. Without those gravitational cradles, gas would have had nowhere to gather. Picture a valley between mountains on a foggy morning. The fog drifts downhill and collects in the lowest points. The valley did not create the fog, but it gave it a place to settle. Dark matter halos are like those valleys. They do not produce stars, but they create the conditions where star formation becomes possible. Over time, small halos merged into larger ones. Galaxies grew through a process of assembly, pulling in gas, swallowing smaller companions, and deepening their gravitational wells. This hierarchical growth is a fundamental prediction of models that include dark matter. It matches what we observe when we look at the distant universe. The earliest galaxies are small and numerous. Later galaxies are larger and more organized. The family tree of cosmic structure reads from many small roots to fewer large branches. This process is not gentle. When halos collide, they do not simply stack neatly on top of each other. They pass through each other, stir orbits, fling debris outward, and gradually settle into a new configuration. Over billions of years, these mergers build layered structures where ancient remnants orbit inside more recently assembled material. Our own Milky Way carries the memory of many such events. The patterns left behind can still be read in the orbits of its oldest stars. On the largest scales, this assembly produces something breathtaking: the cosmic web. Galaxies are not scattered randomly through space. They are arranged along filaments, sheets, and dense knots, with enormous voids in between. Computer simulations that include dark matter produce this web naturally. They start from the tiny density fluctuations seen in the microwave background and run gravity forward for billions of years. The result matches the observed distribution of galaxies with remarkable fidelity. The voids between filaments are not truly empty. They contain thin wisps of gas and scattered galaxies. But compared to the dense filaments and clusters, they are vast deserts. Some voids stretch hundreds of millions of light years across. Their size and shape are another test of how structure grows. The rate at which voids expand depends on how much invisible mass is pulling matter out of them and into the surrounding web. The cosmic web is not a metaphor. It is a measurable structure. Sky surveys that map millions of galaxies confirm its existence and its detailed shape. And the scaffolding that holds it together is invisible. Ordinary matter lights up the web like city lights along a highway at night. But the road itself, the gravitational framework that decides where the lights appear, is made of something we cannot see. Dark matter does not appear to interact with light in any wavelength. It does not emit radio waves. It does not absorb infrared. It does not scatter X-rays. This transparency is not just a curiosity. It is a defining property that separates the invisible mass from everything else in the periodic table. Ordinary matter, no matter how cold or faint, still participates in the electromagnetic conversation. Dust absorbs starlight and re-emits it in the infrared. Cold gas absorbs specific wavelengths and leaves narrow shadows in passing light. Even a lone hydrogen atom in deep space will occasionally emit a radio photon. Dark matter does none of this. It is electromagnetically silent. This silence also means it does not collide with atoms in the usual sense. If invisible particles frequently bumped into ordinary matter, the universe would feel different. Gas clouds would heat in unexpected ways. Stars might behave oddly. Planets moving through the galaxy would experience a subtle drag, like wading through shallow water. None of that is observed. The emerging picture is a substance that interacts through gravity alone, or nearly so. It clumps into halos around galaxies, but it does not collapse into thin disks the way gas does. Gas loses energy through radiation. It cools, sinks, and flattens into the rotating disks we see as spiral galaxies. Dark matter cannot radiate its energy away, so it remains in a more extended, roughly spherical distribution. The halo surrounds the galaxy on all sides. It reaches far beyond the last visible stars, like an invisible atmosphere extending into the emptiness of intergalactic space. Think of it as the difference between a marble rolling on a table and a cloud of perfume filling a room. The marble loses energy through friction and settles. The perfume spreads everywhere and stays diffuse. Dark matter is more like the perfume. It fills the space around a galaxy without condensing into a neat structure. Ordinary matter was thoroughly tested as a possible explanation. Astronomers asked whether the missing mass might be cold gas, faint dust, or dim stars too feeble to detect. The trouble is that ordinary matter leaves fingerprints. Gas absorbs and emits at specific wavelengths. Dust reshapes the spectrum of passing light. Even burned out stellar remnants affect their surroundings in measurable ways. And there is a harder limit. The amount of ordinary matter in the universe was set during the first few minutes after the beginning. Light elements formed through nuclear reactions. Those abundances, combined with the microwave background pattern, pin down ordinary matter's share with high precision. There is simply not enough of it to fill the gravitational gap. The best current evidence suggests that dark matter is cold. In physics, cold does not refer to temperature in the usual sense. It means the particles move slowly compared to the speed of light. This is important because the speed of the particles determines how small a gravitational structure can survive. If dark matter particles were fast, they would stream out of small density peaks before gravity could hold them. Small structures would be erased, like writing in sand washed smooth by waves. The universe would look too uniform on small scales. Instead, we see a rich variety of structure. Tiny dwarf galaxies, small galaxy groups, faint satellite companions. All of these require that the invisible particles were slow enough to settle into compact wells early in cosmic history. Some alternative models propose warm dark matter, where the particles are a bit faster. This would smooth away the smallest structures and might explain certain tensions between observations and predictions. But it must still match the abundance of faint galaxies and the detailed patterns in intergalactic hydrogen. Too warm and the universe becomes too smooth in places where it is clearly textured. Another idea imagines dark matter as an ultralight quantum field with a wavelength that stretches across galactic scales. In that picture, the particles behave more like waves than like grains. Their quantum nature creates a gentle resistance to being squeezed too tightly, which could soften the centers of galaxy halos. Instead of a sharp central peak, you would get a smooth core. Picture the rounded bottom of a bowl rather than the sharp point of a funnel. Yet another possibility is that dark matter particles interact with each other, though not with ordinary matter. Even a modest rate of self-scattering could redistribute energy within a halo over billions of years. Dense centers would puff outwards slightly. The result would be similar to the wave model in some ways, producing softer cores, but the underlying physics would be entirely different. The challenge is that cluster collisions show very little sign of dark matter dragging on itself, which limits how strong this self-interaction can be. Each of these ideas makes specific predictions about how halos should look on their smallest scales. Dwarf galaxies become crucial laboratories because they are dominated by dark matter. Their stars are sparse, so the gravitational field is almost entirely shaped by the invisible component. Measuring how stars move inside a dwarf galaxy is like reading the shape of a bowl by watching how a marble rolls inside it. Some dwarfs appear to have surprisingly little dark matter for their size. That challenges the assumption that every galaxy must sit inside a massive halo. Others are so diffuse and faint that the invisible mass seems to be doing nearly all the gravitational work. These outliers sharpen our questions and push models toward greater precision. The variety of dark matter models also affects what we expect from modified gravity theories. Some physicists have asked whether the missing mass is truly mass at all. Perhaps the laws of gravity change on very large scales. These alternatives can reproduce certain rotation curves without adding unseen particles. But they struggle when confronted with galaxy clusters, where the lensing mass sits in different locations from the ordinary matter. They also face the microwave background, whose peak pattern demands a gravitational component that does not couple to light. Any alternative must pass every test that dark matter passes, not just a few. The Milky Way is surrounded by a family of smaller galaxies. Some, like the Large Magellanic Cloud, are bright enough to see with the naked eye from the southern hemisphere. Others are so faint that they were discovered only in the last 2 decades, hidden in the data of wide-field sky surveys. These satellite galaxies orbit through our halo, and their paths are shaped by the invisible mass surrounding them. When a small galaxy falls into the gravitational field of a larger one, it experiences tidal forces. The side closer to the host is pulled harder than the far side. Over many orbits, these forces can stretch the satellite, strip away material, and eventually tear it apart entirely. Dark matter, sitting in the outermost regions of the satellite's halo, is often the first to go. It is less tightly bound than the stars near the center, so it peels away like the outer layers of an onion. The remnants of these encounters do not vanish. They spread into long, narrow streams of stars that continue orbiting the host galaxy. Imagine dropping a line of paint across a spinning record. The paint would stretch and curve, following the rotation. Stellar streams behave similarly. They arc across the sky, tracing the gravitational field through which they travel. These streams are extraordinarily sensitive to disturbances. If the gravitational field were perfectly smooth, a stream would remain thin and coherent for billions of years. But if small, invisible clumps of mass lurk within the halo, their gravity can punch holes in passing streams. They create spurs or subtle thickening. Each gap or kink in a stream becomes a record of an encounter with something unseen. This turns streams into seismographs for dark matter structure. You do not need to catch a particle in a detector. You only need to watch how gravity has disturbed a delicate ribbon of stars over cosmic time. Observatories that measure precise stellar positions and velocities can reconstruct the history of these encounters. They test whether halos are full of small clumps. That is one of the central predictions of cold dark matter models. The galaxy becomes a canvas, and the streams become the ink that reveals what the canvas is made of. The Gaia Space Observatory has transformed this kind of work. Instead of simply photographing where stars are, Gaia measures how they move. It tracks how stars drift across the sky and how they move along our line of sight. The result is a detailed choreography of nearly 2 billion objects. Those motions respond to gravity, including the gravity of mass we cannot see. Researchers model the orbits of halo stars, globular clusters, and distant companions. From those paths, they infer the shape and extent of the dark halo. Small differences in orbital paths can reveal whether the halo is spherical or elongated, whether it has substructure, and how far it extends. Gaia has turned the galaxy into a gravitational laboratory, using starlight as the measuring instrument. Some stars move so fast that they appear ready to leave the galaxy entirely. These hypervelocity stars are flung outward after close encounters with the supermassive black hole at the center, or with dense stellar groups. Once launched, they race through the outer halo like test probes. Whether they escape or eventually turn back depends on how deep the galaxy's gravitational well extends. If the halo is massive and far-reaching, even very fast stars can be slowed and captured. If it is lighter, those same stars sail into intergalactic space. By measuring the speeds and trajectories of these runaways, astronomers estimate the escape velocity of the Milky Way. That number is a direct measure of total mass, most of which is invisible. Now consider the universe's smallest galaxies. Ultra-faint dwarfs contain so few stars that they barely stand out against the background sky. Some hold only a few hundred known members, spread across a region larger than you might expect. Yet their stars move as if a heavy gravitational hand is holding them in place. The ratio of invisible mass to visible mass in these systems can be staggering, reaching hundreds or even thousands to one. These extreme objects are powerful tests for dark matter models. In a universe where structure builds from small to large, there should be many small halos, far more than the number of observed dwarf galaxies. For years, this mismatch was called the missing satellites problem. Simulations predicted swarms of small companions around galaxies like ours, but telescopes found far fewer. One resolution is that most small halos never formed stars. Intense radiation from the first generations of stars could have heated gas in tiny halos, preventing it from cooling and collapsing. Those halos would be truly dark, containing mass but no light at all. Another resolution is that our census was incomplete. Ultra-faint dwarfs are hard to spot, and every year new ones are added to the list. The puzzle keeps evolving as surveys grow deeper and wider. A related tension involves the internal structure of predicted halos. Some of the most massive predicted subhalos should be dense enough that forming stars within them would be almost unavoidable. Yet the bright dwarfs we observe do not always seem to live in halos that dense. This is called the too big to fail problem, because those halos seem too substantial to have failed at galaxy building. Possible explanations include bursts of star formation that rearrange the inner mass. Tidal interactions with the Milky Way could also have reduced central densities. The core cusp debate is closely related. Simple simulations often produce halos with steep central density peaks called cusps. But observations of some dwarf galaxies suggest gentler, flatter cores. If the difference is real, it could point to new physics. It could also reveal the long-term influence of ordinary matter. Repeated cycles of gas inflow and expulsion, driven by stellar winds and supernovae, can reshape the gravitational potential. Stars are not passive residents. Massive stars pour radiation into their surroundings. When they die as supernovae, the blast wave shoves gas outward with tremendous force. If this happens repeatedly in a galaxy's center, gas is pushed out and then falls back, and each cycle changes the gravitational potential. Dark matter responds to those shifts. Over many episodes, the invisible particles can be nudged onto wider orbits. The central density drops. A cusp softens into a core. This feedback mechanism offers a way to reconcile steep predictions with flatter observations without invoking new fundamental physics. Galaxies with bursty star formation histories should show the most reshaping. The tiniest dwarfs that never hosted many stars might preserve their original inner profiles. The bullet cluster offers a different kind of evidence. It is a system where two galaxy clusters collided at enormous speed. During the collision, the hot gas in each cluster crashed together and slowed down, because gas interacts through pressure and friction. The galaxies, separated by vast distances between their stars, mostly pass through each other, and the majority of the mass, mapped through gravitational lensing, followed the galaxies rather than the slowed gas. That separation is striking. It shows that most of the weight in the system behaves like something that does not collide or lose energy in the usual way. It passes through the crash site cleanly, like a shadow that cannot be stopped by a wall. The hot gas, glowing brightly in X-ray observations, marks where the collision actually happened. But the gravitational center, mapped through lensing, has already moved past that point. Similar merging clusters have been found, each providing another test of whether the invisible component truly behaves as a collisionless substance. Across different collision speeds and viewing angles, the pattern holds. The bulk of the mass avoids the fate of the gas. Underground, far from the noise of cosmic rays, some of the quietest rooms on Earth are listening for the faintest possible signals. These are direct detection experiments. Their goal is simple in concept and extraordinarily difficult in practice. They want to catch the moment when a dark matter particle nudges an atom. If the Milky Way is surrounded by a halo of invisible particles, then Earth is constantly passing through that halo. Billions of these particles could be streaming through your body every second. Almost none of them interact with anything. They slip through rock, water, metal, and bone, as if matter were not there. But if the interaction rate is not exactly zero, something rare can happen. One particle might tap a nucleus and transfer a tiny amount of energy. That tap is what detectors are built to sense. Liquid xenon experiments are among the most sensitive. Xenon is a noble gas that can be cooled into a dense liquid. When energy is deposited inside it, the xenon produces a flash of ultraviolet light and a small burst of freed electrons. The flash and the electrons are detected separately, and the timing between them reveals where inside the detector the event occurred. The pattern on the sensors tells you the depth and the position. This three-dimensional reconstruction matters because backgrounds cluster near the walls. The cleanest, quietest region is deep in the center of the detector, shielded by the xenon itself. The experiments operate like listening rooms. Every component is selected for ultra-low radioactivity. Surrounding shielding blocks stray particles. Active veto systems tag anything that enters from outside. The goal is to understand every single background event so well that anything unexpected stands out like a whisper in a silent cathedral. Another approach uses crystals cooled to temperatures near absolute zero. At those temperatures, a tiny deposit of energy creates vibrations called phonons, which are essentially sound at the atomic scale. Sensitive thermometers on the crystal surface can detect the resulting change. Some designs also measure the freed electrical charge, which helps distinguish a nuclear recoil from an electron recoil. The combination gives powerful background rejection, especially at low energies, where some models predict signals. Imagine placing your palm flat on a perfectly still drum skin. If someone dropped a grain of sand from a great height, you might feel the faintest thud. Cryogenic detectors work on a similar principle. The drum is a crystal. The grain of sand is a dark matter particle, and the sensitivity is refined to an almost unimaginable degree. One intriguing strategy is to search for an annual modulation in event rates. Earth orbits the Sun, and the Sun moves through the Milky Way's halo. In one part of the year, Earth's orbital velocity adds to the Sun's motion through the dark matter wind. 6 months later, it partially subtracts. This should create a small seasonal rise and fall in the number of detected events. The appeal is that most backgrounds do not naturally follow this same pattern with the same phase and period. A consistent annual signal in the right energy range would be compelling. One experiment in Italy has reported such a modulation for many years, but other experiments using different materials have not seen a compatible signal. The debate continues, and it pushes the entire field toward more rigorous seasonal and environmental controls. If dark matter particles are their own antiparticles, two of them meeting could annihilate and produce high-energy photons. Space telescopes can search for these gamma rays, focusing on regions where the invisible density is expected to be highest. Dwarf galaxies are particularly attractive targets because they are rich in dark matter and have little other gamma ray activity. The center of the Milky Way is also of interest. It is a complicated region with many astrophysical sources that can mimic a particle signal. Some candidates might decay very slowly, producing faint X-ray photons over cosmic time. Galaxy clusters, with their enormous reservoirs of invisible mass, are promising places to look for such a signal. A narrow spectral line at a specific energy, appearing consistently across multiple targets, would be extraordinary. It would mean the hidden mass is not entirely silent. It occasionally whispers light into the universe. Collider experiments take the opposite approach. Instead of waiting for dark matter to come to us, they try to create it. In a particle collider, enormous energy is focused into tiny volumes. If dark matter particles can be produced, they would escape the detector without leaving a trace. Physicists look for events where the visible products do not balance, where momentum seems to be missing. That imbalance could be the fingerprint of something invisible, carrying energy away. The Large Hadron Collider has searched for these signatures across many channels. So far, no clear signal has emerged. That absence is not defeat. It is a narrowing of possibilities. It tells us that if dark matter can be produced in collisions, it couples to ordinary matter more weakly than the simplest model suggested. The remaining territory is still vast, and future colliders with higher energies or different strategies may reach deeper. Among the leading candidates is a class of particles called axions. They were originally proposed to solve an unrelated puzzle in the physics of the strong nuclear force. The solution predicted a new particle that would be light, stable, and extraordinarily difficult to detect. Those properties also make it a plausible dark matter candidate. Experiments search for axions by building resonant cavities. It is like tuning a radio to a very specific frequency. you listen for the faint signal that a cosmic sea of axions might produce in a strong magnetic field. What makes axions captivating is the double reward. Finding them could solve two mysteries at once, one about the symmetry of the strong force, another about the missing mass of the universe. It is rare for a single discovery to close two open doors simultaneously. Other candidates include sterile neutrinos, which would be heavier and quieter cousins of the familiar neutrinos. They would interact almost exclusively through gravity and through subtle mixing with ordinary neutrinos. If they exist with the right mass, they could contribute to the invisible mass budget and leave faint traces in X-ray observations. Primordial black holes are another possibility. These are not the black holes formed from dying stars. They would have been created in the earliest moments of the universe. Regions of unusually high density could have collapsed directly under their own gravity. If enough formed in the right mass range, they could account for some or all of the missing mass. Observations constrain this idea from many directions. Too many black holes of certain sizes would disrupt visible systems or produce detectable lensing events. But windows remain open, and the concept keeps drawing attention because it replaces exotic new particles with an extreme application of known physics. The future of the search is rich with promise. New surveys will map billions of galaxies, refining our picture of how the cosmic web grew over time. The Vera Rubin Observatory will track changes in the sky with unprecedented consistency. It will improve weak lensing measurements and discover faint satellites and stellar streams that test halo structure. The Euclid space mission will measure galaxy shapes from above the atmosphere, building a three-dimensional map of gravitational lensing across cosmic time. The Square Kilometre Array will trace hydrogen across vast volumes of space, using radio waves to outline the gravitational scaffolding of the universe. Each of these projects approaches the mystery from a different angle. Together, they will tighten the constraints on what dark matter can and cannot be. They will test whether halos have the predicted internal structure. They will check whether cosmic structure grew on the expected timeline. And they will watch for subtle deviations that point toward new physics. If the particle is identified, the consequences will ripple through every branch of physics. The cosmic budget will shift from a confession of ignorance to a statement of substance. Galaxy formation models will gain a real microphysical foundation. The standard model of particle physics, one of the most successful theories ever built, will need to expand. New symmetries, new forces, or new fields may be revealed. The word dark will lose its vagueness and become a name with properties that can be written down, tested, and taught. Until then, the search continues. It is patient, careful, and strangely beautiful. Astronomers watch the sky. Physicists listen underground. Theorists explore the space of possibilities. And the universe keeps turning, holding its secrets in gravity and silence. As we come to the end of this journey, take a moment to notice how far we have travelled. We began with the simple pull of gravity. We followed it outward through spinning galaxies, ancient light, and the vast web that stretches across the observable universe. We drifted through ideas born almost a century ago. We followed careful measurements of starlight into quiet rooms where the most sensitive instruments on Earth wait in silence. Again and again, the same story appeared. Something unseen is holding everything together. It guided the first gas into the first gravitational wells. It shaped the growth of galaxies across billions of years. It bent light around clusters and left its signature in the oldest glow the universe has ever produced. From the smallest dwarf galaxies to the largest surveys still being built, its influence connects every scale into one unfolding pattern. You do not need to remember the details. Let the names and numbers fade like distant echoes. What remains is a feeling. The universe is deeper than it appears. Much of reality reveals itself only through patience, through careful listening, and through a willingness to look beyond what shines. That is a comforting thought. The cosmos holds more than meets the eye, and that hidden depth is not something to fear. It is something to rest inside. Notice your hands. Notice where your body touches the surface beneath you. Let the weight of the world settle, and let your breathing carry you downward into stillness. The galaxies will keep turning. The experiments will keep listening. The answers will wait. If you enjoyed this journey, you might like to explore another before sleep fully arrives. And if you feel like it, liking or subscribing helps others find their way here as well. For now, let the darkness feel spacious rather than empty. Let your thoughts slow with the turning of the stars. Sleep well and good night.